This video is how we get from this egg carton design here to the ANOVA summary table. And I'm going to show you the long way. I'm going to show all these steps, and that way you can see where these numbers actually come from. And the first thing that I would do is take these individual values, right? So this is a male that had 10 grams of medicine here, and he took 12 minutes to fall asleep. This female here had 10 milligrams of sleeping medicine and took 48 minutes to fall asleep. This male here, for example, took 12 minutes to fall asleep, and he had 40 milligrams of sleeping medicine. So I stacked these on top of each other. I went by males first and then all the females. So we stacked them on top, and then I copy pasted them up here. So I'm gonna show you first. We're gonna calculate at the sum of squares within. So we have here the person 1, 2, 3 all the way to 24, and then what we have as well is the gender. 1 is male, 0 is female. Then we have the dosage, 10 milligrams, 40 milligrams, 70 milligrams. Then it repeats again, 10 milligrams, 40 milligrams, 70 milligrams. So the first person 1, is a male, has 10 milligrams dosage, and took 12 minutes to fall asleep. Person number 9, 1 is a male, has 70 milligrams, and took 19 minutes to fall asleep. Person 20, 0 here, is a female, 40, had 40 milligrams of the dosage, and 25 took 25 minutes to fall asleep. So the first thing that we do is calculate the group mean, because we want to look at the variation within each group. Right? Remember, this is the measurement for the random error or the sampling error. So we're going to look at how much does each group vary within each group. So we calculate the average for D4 through D7. So this is the average for this first group of men that had 10 milligrams of the dosage. And you can see, in average, this group took 14.5 minutes to fall asleep. The next group, this would be here D8 through D11, is the group of men that had 40 milligrams of the dosage. So they took 10.5 minutes to fall asleep. And we do this for each group, and we do the same thing. This is exactly the same thing that we did in OneWayANOVA, right? We calculate the difference of each individual score, 12 minutes, to the group mean, right? So this group here is the females that had 40 milligrams of the dosage. So here the difference is this woman's individual score minus her group mean. Gives you 12.275 minutes, so she stayed awake longer than her average. Then we square all these differences and we get the sum of squares within. We transfer this into our within groups sum of squares in the table. The degrees of freedom is 18 because it's n, the total sample size, 24, minus k, the number of groups. So there's 6 groups. Right? K is the number of groups, and we're gonna get on with the next one. We're gonna go to the main effect gender. Now this is the same thing that we did for the between groups effect in the OneWayANOVA, right? But this time we use the mean of the group gender, and we compare it to the grand mean. So that's the total average. This is the average of all the people in the study, which we call the grand mean. And then here we have the average for the men, and then we have the average for the women. Okay, and we calculate the difference between the mean of the gender and the grand mean. We square it, and we add it all up. So you see the men fall asleep faster. They're minus 7.71 minutes below the average, the grand mean, and the women fall asleep less fast, like they stay awake longer. They're 7.71 minutes above the average. We add all these, we square these differences, we add them all up, and we get 1426. So we enter this into the main effect gender here. The degrees of freedom are the number of levels minus 1. Number of levels here are 2, right? Male, female, minus 1 is 1. Sum of squares divided by 1 is the same number, 1426. And here, to get the F ratio, we divide the 1426 by the mean squares within. Right? And mean squares within we got by dividing the sum of squares divided by degrees of freedom gives us the mean squares. So same principle as in the one-way ANOVA. Time to move on to the next effect, the main effect for dosage. So as we did for gender, we put in the grand mean, but now we calculate the average for the dosage. So this is the 10 milligram average. So we have this and these guys together. Right? Click on here, gonna go over, and we have the 10 milligram group, the blue one, and the other 10 milligram group, the green one. Right? Basically, the men who had 10 milligrams and the women who had 10 milligrams. Right? And then we do this. Then we have the next group here, these guys and these guys. Those are the 40 milligrams, and then these guys, these men that had 70 milligrams, and these women that had 70 milligrams. We look at how these groups differ from the grand mean. Here the difference to the grand mean, and then the difference squared. We add it all up, we get 835.75. So this is the sum of squares for the dosage. Degrees of freedom is number of levels minus 1. So here we have 3 dosage levels, 10, 40, and 70 milligrams. So 3 minus 1 is 2. And to get the mean squares, we divide 835 divided by 2 is the 417. To get the F ratio, we do the same thing again. 417 divided by 70 gives us this F ratio. And then, by the way, here to get the probability, we use the F-dist formula. We give the values, so the 20, that's the F value, and then we have to say what's degree of freedom 1 and what's degree of freedom 2. So degree of freedom 1 is from the gender main factor, and degree of freedom 2 is from the within groups factor. Same thing here, F-dist, this time X is the 5.92, and the degree of freedom 1 is the dosage degree of freedom, the degree of freedom factor 2 or factor B, and then the other degree of freedom is from the within group. Now we get to the last effect here, that's the interaction, and this is the trickiest one to calculate, because here for the interaction effect we calculate the mean for the gender group, the mean for the character group, and the grand mean. And what we do to get our formula, we take the group mean, so that's the blue group here, or the red group, or the purple, the group mean, minus the mean for the gender, green one, minus the mean for the dosage, minus the grand, plus the grand mean. So this is the formula to get the deviant score for the interaction. Then we take these values, square them, add them all up, and we get 14.58. So this is the interaction sum of squares, 14.58. The degree of freedom is degree of freedom rows times degree of freedom column. So this 2 is 1 times 2 is 2. Mean squares is 14.58 divided by 2. And then this gives us an F ratio of 70 divided by 7 divided by 70 gives us 0.10. Right? Every once in a while the number goes low, goes close to 0. But usually it shouldn't go too far below 1. And as you can see, the probability here goes very high, 0.90. So it's highly unlikely that there's a difference here in the interaction. There's no significant effect. Alright, so this would be the two-way ANOVA, and what we could conclude from these results is that gender is significant, so there's significant differences in gender, and then also there's significant differences in the dosage. Both of these F ratios are statistically significant because they're below the 0.05 significance level. If we had set our significance level at 0.01, this dosage level would not be significant, it would barely miss the significance level. Now, in gender, we only have two groups, so you know exactly that the difference can only be between those two, so we know there's a statistically significant difference between the genders. However, in the dosage, we don't know exactly where the difference is at, and we would have to conduct post hoc tests to explore where the differences are between those two dosages.